Hey team, this is a video all about some core math review topics that are helpful to know because we're using these skills all throughout the school year in our AP Physics 1 course. Now, I kind of have it broken up into 4 different topics, okay? Kind of from the easier to the more difficult, or maybe from the ones where not everyone necessarily has to review it to ones that are really important. And what determines whether you review A and B versus just C and D? To be honest, it probably has to do more with math level more than anything else, okay? It's optional, and if you're in my own personal class, I'm never going to check to see which particular sections you actually looked at, but like, if you already finished calculus, so you're here at the bottom, to be honest, maybe it'd be helpful to review A and B, but if you've already finished calculus, you've been doing A and B inherently for years, I don't think it's needed. Whereas, let's say you're in my class after having completed Algebra 2, I would strongly recommend you look over A and B as well. Now, I'm not saying like I'm introducing new material. It should all be stuff when you're watching it like, oh yeah, that's right. Just kind of jogging your memory. That's the idea. This is not new math topics, regardless of your math level. But these are things that we're doing pretty often. And to be honest, things that I'm not really, if you're in my own class, going to be stopping and explicitly talking about. So you should know how to do these things, okay? Anyway, you should be able to jump around based on whatever section you feel is most appropriate for you. Let's go ahead and get started. We're going to begin with some algebra stuff, some basic algebra things that I notice. And the first one is when we have to solve for something in the denominator of a fraction. The denominator means the bottom part of a fraction. So here, the equation source isn't important. It turns out this has to do with something that's moving in a circle. So the acceleration of an object moving in a circle, it's based on its velocity, which is raised to the second power, and r. Let's say we were trying to solve for this, the radius. How do I go about solving for the radius in this problem? The radius is in the bottom. Now, the algebra step, this is hopefully what you remember, especially after watching this. If I want to get rid of this thing in the bottom, I don't just divide by v squared. I see some students do that. They just kind of try to get rid of this thing. But that's still going to leave you with 1 over r. No. We need to get r out from underneath. So if you multiply both sides by r, so if I multiply the right side by r, well, this is basically like it's in the top, so I have r divided by r. That cancels. And of course, from algebra, if I multiply the right side by r, I have to multiply the left side. So that leaves me with r times a equals v squared. And then I could go about finishing. If I want to solve for r, maybe I divide both sides by a. Bam. R is equal to v squared divided by a. That's how you solve it. If you want to get something that's in the denominator all by itself, you first got to get it out of the denominator. And that's almost always going to be you then multiplying both sides by that thing that's in the denominator, okay? Now, moving on, how do we deal with squares and square roots, all right? Now, let's say, again, I'm here in this same equation. Let's say I was trying to solve for the numerator, this thing v squared. I'm in purple here, okay? Well, now I want to solve for this thing in the numerator. I don't want it divided by r, so I'm going to multiply both sides by r, kind of similar to what we did before, but now it's just to get it out of there. So r times a is equal to v squared. But in this case, I don't want what v squared is. I want to solve for v. So how do I get v all by itself? You take the square root of both sides. And make sure you're doing the whole thing on the other side of the equation. The way you undo squareds is by taking the square root. The square root of v squared is just going to leave you with v. And that means on the other side, I have root r times a. And again, just be careful, both r and a are underneath that square root sign. You're taking the square root of the whole left side and the whole right side of the equation, okay? Let's go over here. Let's say I was trying to solve for m. Okay, now this one's a little tougher, and to be honest, you could do it a few different ways. Maybe first, if I'm trying to solve for m, let's get rid of this 2 pi thing. So let me divide both sides of 2 pi just to get it out of there, because again, I just want m all by itself. Ultimately, I want something that looks like this. M equals and a whole bunch of garbage over here. So I'm going to divide both sides by 2 pi. That's going to cancel it out there. So t divided by 2 pi equals the square root of m over k. Well, okay. Now, how do I get rid of this square root? Well, I square it. The way I undo a root is to raise it to that power. And if I square the right side, I have to square, I square the right side, I have to square the left side. So I'm going to come on over here. Okay, now, important. Everything on this side is being squared. T squared divided by. Students mess up. They don't square the stuff on the bottom. 2 squared is 4. Pi squared is pi squared. What does that equal? I got rid of that square root, m over k. And then again, if I was trying to solve for m, I just want to kick this k out from underneath. That leaves me with t squared multiplied by k over 4 pi squared. That is equal to m. Okay, so remember, if you're either going to do the square roots or the squares, more than anything, remember, you got to apply that to every variable that's on whatever side of the equation. Students seem to forget how to do that. Okay? All right, that's it for the algebra stuff. Let's continue on. Let's look at some angles and some triangle things, okay? So first, I have this example, and I have these two parallel lines. M and N are parallel, all right? And then I have this diagonal line. It's straight, but it's diagonal, okay, going down. Let's try to figure out what these other angles are. I'm telling you here that A is equal to 75 degrees, okay? So how do I figure out what these other angles are? You could pause the video if you want to start, but I'm going to run through it. Now, if I know that this angle A is 75, D is something known as a vertical angle. Vertical angles are equal. So if A is 75, that means that D is 75. Also, from here to here, that's just a straight line. That should add up to be 180 degrees. So what does B have to be? B has to be 180 degrees minus 75. That's how I figure out what the value for B is. So 180 minus 75, that leaves me with 105, 105. And then if I know what B is, B and C, again, those are vertical angles. Those are the same thing. So they have to be the same value. Okay, now the tough one. How do I then start figuring out what's going on with E, F, G, and H over here? Oh man. I'm going to flip colors here to green. A, right here, and let's see, I have A and I have E. A and E, oh, am I remembering my trigonometry jargon? These are alternating interior angles. A and E should be the same value by geometry. To be honest, now that I'm thinking about it, I think it's D and E. Those are our alternating interior angles. Oh, I make mistakes just like everybody else. D and E, those are alternating interior. So those need to be the same. So if D is 75, E is 75. Okay, so now I know that E is 75. H is vertical, so it needs to be the same. That's 75. E and F, I have the same situation as before. Those have to round out my other two for the same reasoning as before. So there are times in this class where remembering some geometry, like triangle geometry and like these parallel line geometries, are going to be important. Speaking of triangle geometry, here's another problem. Let's try to go about filling in these other letter angles, knowing here that theta is 37. Again, maybe you pause it and you try it on your own. Okay, now this right here that I'm shading in, this is a triangle. And the angle of a triangle always has to add up to 180 degrees, always. So this here is a 90-degree angle right here. This is theta, and I know theta is 37. So my first step, maybe there's other ways to do this, but I'm going to find this angle. I know that in total, everything has to add up to be 180. So if I subtract the 90-degree angle here and the 37-degree angle that's right here, what's left, that has to be this angle at this spot right here. Doing that gets me an answer of 53 degrees. So I'm going to do a little erasing just to clean this up a little bit. I just figured out that this angle right here is 53 degrees. Now, B and this angle, those are vertical angles. So that means B is 53 degrees. Ah, okay. Also, look right here. B and A, that's 90 degrees. I know this because this dashed line is 90 degrees with respect on this side here, so it has to be the same over here. So B and A have to add up to 90. So 90 minus 53, that gives me 37 again. Ah, so A has to be 37 degrees. A and D, those are vertical angles. That means D is 37 degrees. What's C? Oh, well, CO, this is also vertical angles. This is again going to be 90 degrees for letter C, okay? These can be tough, and we're actually going to see this example in a few weeks when we talk about objects sliding down ramps. Next part of a little bit of trigonometry and geometry. We're going to do some right triangle trigonometry. Remember SOHCAHTOA. We use this a lot, especially, or I should say, really early on. In the next couple of weeks, we're going to start using trigonometry. Now, we're just doing kind of basic SOHCAHTOA stuff, nothing too tough, but make sure you remember how to do these, all right? So here I have a triangle, and I know this angle. It says it's 30 degrees. I also know this. This is the hypotenuse. That's 12 meters. How do I figure out y and x? SOHCAHTOA means that the sine of theta is equal to the opposite over the hypotenuse. What does opposite mean? If this is my angle here, theta, opposite, that's the side of the triangle that's opposite. That would be y. Hypotenuse, that's just the hypotenuse of the right triangle. That would be this 12 meters. So let's say I was trying to solve for y. Okay, y, I think in my head, okay, y is here. It's on the opposite side, okay. And then, I know the hypotenuse, opposite and hypotenuse. So, okay, to figure out y, I'm going to go like this. I know that the sine of theta is the opposite over hypotenuse. If you don't remember this, or maybe I should say if it helps you to write it down, I love it, go for it. So the sine of 30 degrees is equal to opposite, that's y, divided by the hypotenuse, that's 12. So how do I solve this equation? Now I just have an algebra equation. How do I solve this for y? Multiply both sides by 12. So y is equal to 12 times the sine of 30 degrees. In this class, we're always using degrees, always, okay? Now, if you don't remember that sine of 30 is 1/2, that's okay, use your calculator. But if you punch this into your calculator, you should get that y is equal to 6. So the answer there, bam, it's 6, okay? Let's try to figure out x. X is right here. This is the side of the triangle that is adjacent. Well, cosine, that's adjacent divided by hypotenuse, just like that. So the cosine of 30 degrees, because that's the angle, that's the adjacent side, x, divided by the hypotenuse side, that's 12. Rearrange. Okay, that's going to be 12 times the cosine of 30 degrees. Cosine of 30 is what? Root 3 over 2. Punch it into your calculator. I get an answer for x of about 10 point. I'm going to look off and glance at my piece of paper. 10.39. 10.39. Rounding to 1 or 2 decimals is fine. So remembering sine, cosine, tangent, SOHCAHTOA is important for this class to solve for things, as well as the Pythagorean theorem, the idea of a squared plus b squared equals c squared. I don't have a problem here, but that's an important thing to remember as well, okay? Let's jump into graphs, letter C. Okay, first, reading graphs. Now, yeah, in physics, you're going to get some kind of nice-looking, clean-looking graphs with straight lines, but I like this example here because it's showing kind of a complicated graph that has a lot of maybe interference. So, real quick, how do we read it? This question says, how much force, and this is a force, always read the axes, it's showing the amount of force that's applied over a certain amount of time. So this first question is asking how much force is being applied at the 5-second mark. So 5 seconds, okay, I go to that spot on the x-axis, I go up, and right about here, what does that look like? It looks like it's about 15. Again, this is a messy graph, so sometimes you got to use your noodle. Okay, what would be the approximate value? It looks like it's maybe slightly below 15. If you put 14.9, that's okay. If a graph looks like this, if it's a little messy, obviously there has to be a little bit of acceptable error. Like if this was a quiz question, I would have to accept 14.9, 14.8, 15, because it's so close. You got to do a little bit of adjustment or estimation, and that's totally fine. Next question, what time is there 7 newtons of force? Okay, so now I'm being told there's 7 newtons of force. Okay, where would 7 be? Here's 5, here's 10, so 7 would be kind of right. Let's see, can I get a new pen color? 7 would be right around here. Okay, so let's see, that's at this spot. Okay, what time is that? Maybe 1.5 seconds, maybe a little less, 1.4. Again, if you thought 1.4 or 1.5, 1.3 is okay, around there. Okay, this was in newtons. This is going to be in seconds. It's always good to average, or I'm sorry, you should label the measurements that are in there, okay? And then I'm not going to answer letter 7, but why in general could graphs be messy? At least I'm not going to write down an answer. Maybe it's because we're using a sensor, and sensors can always pick up interference. Maybe there's things that get in the way. So this is a graph that you will see sometimes, and again, estimating is fine, but again, sometimes we'll see graphs that kind of have nice, cleaner, straight lines, makes our lives a little easier. we're still looking at graphs right now, but this is kind of slightly different. This is really what do you want to do when you are constructing a graph? Especially, really, this is geared towards when we're doing labs, okay? So some key things, when you're making a graph, you'll want to make sure you're including these. While I didn't make this graph, this is not directly from my class, but this is an example graph from an AP class, and it does a good job matching these things, okay? Now, first thing, you want to make sure when you make a graph that you have your two axes, your y-axis and your x-axis, make sure they're labeled. Did you measure force and distance? Did you measure distance and time? Velocity versus radius? I don't know. But make sure you have them labeled. This example has the mass of a sample and the volume. They have that nice and labeled. Also include the units. They were measuring mass in kilograms. They were measuring the volume here in what? It looks like cubic meters, okay? So make sure you're including the units as well. Now, also, the axes need to be evenly scaled. If you look at this y-axis, it goes 20, 40, 60, 80, 100. Perfect. Amateur move is when students just write down like their data points. Like, oh, the first data point was 2, and then the next data point was 8, and then the next one was 35. Don't do that. You need to figure out the scaling that's needed so that your scale, your graph axes are nice and even. 20, 40, 60, that's nice and even. They don't have to be the same spacing. If you notice what they have on the x-axis, that's a different scale. But again, it is even 0.01, 0.02, 0.03. Very important in this class, always. We're not going to be doing like logarithmic graphs. We're always going to be doing graphs where the axes should be scaled linearly and nice and evenly, okay? Now, we're also not going to do broken axes. Now, to be honest, that's not always terrible. You're not doomed if you do that, but worst case scenario, you might end up doing some math wrong when we do some calculations. Best case, it might be confusing when someone, either in your group or even myself, is looking over your graph and I don't recognize that you have broken axes. So we're not going to break axes. We're basically always going to start at 0. Okay, same thing on College Board, they don't want you to break the axes. Also, when we are making our data points, we always want to draw a line of best fit. So the individual data points, that's what these dots are right here, okay? Now, each of these represents like one trial. And in science, we want to find an average because someone may have messed up in one trial. The way we do an average kind of visually on a graph is you draw a single straight line that approximately has half the data points above or below. Sometimes you might do a graph where you're trying to sketch a curve, but that's pretty rare. Most of the time, it's going to ask you for a line of best fit. You just take a ruler, you kind of line up the edge of the ruler. So again, approximately half the points are above or below, and then you draw a straight line. Team, in this class, we are never connecting the dots. Okay, this is why I wanted everybody to read this. If you are ever connecting the dots, if we have a graph that looks like this, and you go like this, boink, 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 boink. Team, we're not in elementary school. We're not doing one of those connect the dots games. We're drawing average lines. You're never connecting the dots in this class. A straight line of best fit, okay? Oh, when we're finding the slope, so this is kind of like two things in one. Let's remember how to find the slope of a straight line and how that comes into play when we're making our graphs for like a lab, okay? The slope of a straight line, the slope, sometimes that's represented with the symbol m. That's equal to the change in the y-axis divided by the change in the x-axis, or y2 minus y1. If you remember this from like algebra class, x2 minus x1. You do not necessarily have to write this out, but I should see, if this is a lab or this is like a math problem, I should see how you're finding the slope, okay? This person in this graph, they have the slope happening right here. You don't have to necessarily worry about all the specifics. This was a graph of voltage and current, but they did show, okay, this is what they wrote down on their paper. The slope is the change in y, that's the voltage, divided by the current, that's delta, current is I, not that that's important right there. And then what did they do? They picked points on the line, okay? So first, when you're finding the slope, it's the change in y over the change in x, or rise over run, okay? You're looking at the slope of that straight line. I should see some math work. I don't need to see every little bit, but I should see that you're looking at the y-axis divided by the x-axis at minimum. That should be clear. Team, this is the mistake that students make in labs. after we've plotted our data points in a lab and we've drawn our line of best fit, if the lab, which is pretty common if you're making a graph in a lab, if the lab asks you to find the slope, or if you just need to answer whatever the question is, when you find the slope, you are picking 2 points that are on the line that are not your data points. What do I mean? Okay, this student, they circled their data points. That's what all these circles and dots, you don't have to put a circle around it, okay? But these were their individual data points. And then the straight line is when they took that ruler, like I said in the last page, and they roughly estimated half above, half below, they drew a straight line. When you find the slope, you pick 2 lines, or you pick 2 spots on the line. Again, the line represents the average. We want the slope of the average. An individual data point, this spot right here, is not particularly special. Maybe somebody nudged the table when they took those measurements. This spot right over here is not particularly special. Maybe somebody forgot to start the timer. So if you use those data points when you find the slope, you're not using the average. And you're putting really weird emphasis on these 2 specific data points while ignoring all the others. So team, always, when you're finding the slope from a graph that you made with data, you do not use your data points. And this student, if you hit pause and if you really zoom in here, not that you need to, they picked a spot right here and they picked another spot right here, spots that were not their data points. I'm going to try my best to remember this when we do our first graph in lab like this, but hopefully you remember, and hopefully you've done something similar in past science classes. You don't pick your data spots. Okay, team, we're in the home stretch. This is the last letter, letter D, proportions. The first thing I want to talk about is this idea that an equation, it tells us information. Equations are kind of like physics stories. This is a story right here in this equation about velocity, okay? The velocity, and velocity for this video is basically the same thing as speed. The speed of an object, the velocity of an object, it is based on, it is equal to the distance an object travels and the time. What time? The time to travel that distance. That's our story. That's what this equation tells us. Oh, how fast an object goes? It depends on how far it travels and the time it took to travel that distance, how far that was. That's the idea. The other thing to recognize is that we can then use this equation to kind of analyze different scenarios. For example, here's my equation. Let's say I have an object that has a certain velocity, and then another object, well, let's say it travels a larger distance, okay? If it traveled a larger distance, that means the numerator, the top part of the fraction, is bigger. Tell me, what happens to the overall result if I make the numerator bigger and bigger and bigger? I'm just kind of making up numbers here. What happens to the overall answer, the overall fraction, when the numerator gets bigger? The overall value increases. 9 over 2 is bigger than 7 over 2, is bigger than 5 over 2. When the top increases, the overall result increases. So that means if I have 2 similar scenarios, let's say I have similar cars, let's say we're looking at the same 1 hour, the same amount of time. Well, if one car traveled more distance in the same amount of time, that must mean its velocity, oh, it was bigger, the overall result. Another way, simple. If the numerator gets bigger and bigger and bigger, as it's saying here, as D increases, as the numerator gets bigger, the overall result gets bigger, okay? So that must mean that as the distance is increasing, the velocity is increasing. Let's look at this example here. I'm going to flip over to white, number 2 here. It says, here's the same equation. As the time, that's in the denominator. What happens when the denominator gets bigger and bigger and bigger? As t increases, the overall result decreases. It's the opposite. When the bottom part of a fraction gets larger and larger, that means I'm dividing it more and more and more. I'm dividing it into smaller and smaller pieces. So if the denominator in an equation is getting larger, the overall result is getting smaller. That's a core idea. Okay, you should be able to answer questions like that. Here's another equation. Let's say I have the current in a wire is equal to the voltage divided by the resistance. Well, if I increase the voltage, what happens to the current? If the top increases, the overall amount increases. I goes up. If I have this equation and I tell you that there's now more and more resistance, what happens to the current? If the bottom goes up, the overall result goes down. So there's kind of like similar relationships and opposite, inverse relationships. That's what this is really getting at, okay? So it's one thing to describe them. We can also do some mathematical analyses, and this is really the last hurrah, the last part of this video, okay? So it's the same equation. I'm looking here at this top white rectangle, okay? I have that v is equal to d over t. I could ask a question like, what happens if the distance doubled? What happens if I double the distance? What happens to the velocity? We'll assume I keep everything else the same, so I'm not going to change time, same time, but I'm going to double the distance. What happens to the velocity? Does it go up? Does it go down? And by how much? There's a way you can do this, and I kind of have it written out right here. This is my approach. The original equation is this, v equals d over t. This is a question asking me to change my equation. I want the velocity, I want the distance to double. See what I did here? I just rewrote the equation and I plugged in 2 times the distance. Why 2? Because it's asking me to double it. Doubling means I do it 2 times. Well, okay, now let's compare. Let's compare my new equation with my old equation. In the old one, I had distance and time. Oh, I still have distance and time. But look, now I have an extra 2. Now I am multiplying this by 2. It's twice as much as the old version. So if I double the distance, the velocity is twice as much. It's very possible some of you just thought of this answer immediately in your head. Very possible, okay? This right here is a little bit of a proof, kind of how you know, okay? If you weren't sure how to do this, well, writing it out like this could be helpful. Let's try this bottom one, okay? Now it says that v triples. I'm going to go over to white, and I know I'm kind of flipping direction here, but I'm going to do the white part here. So the old version, v equals d over t. The new version, I'm going to triple the time. So instead of t, I'm going to have it be 3t. So velocity is equal to d divided by 3t. So now what has happened? D and D, that hasn't changed. T and T, that hasn't changed. But now I'm dividing. I have that original, but it's being divided by 3. That means it's 3 times smaller. That might be what I write down, 3 times smaller. You could say 3 times as much, okay? But now I'm dividing it by 3. We're going to see some more complicated examples of these proportions as we go, okay? But that's the idea, being able to analyze these equations, not really plugging in numbers, like not really plugging in like numerical numbers like we often do, but just thinking about what happens if one value gets larger or smaller and how that can affect our equation. Okay, but that's it for our math review. Thanks a lot for watching. Hopefully this was helpful.